Hello everyone and welcome to new discussion on this Geographic Information Systems course, and today we are going to discuss georeferencing and also people call as geometric corrections and by many other names, but currently the most popular name is georeferencing. As we have been discussing that basis of GIS is basically mathematics, and various tools which were available in mathematics, many of them have been implemented into GIS. Though we do not directly drive the equations or any other thing, but we use that mathematics, and in order to understand all these intricacies in GIS, how these things works, we have to sometimes go through some equations, and the mathematics which we are using in GIS on regular basis is like a geometric coordinate system, coordinate geometry, the entire subject of mathematics which is being used here directly. Then if you recall that in our CBSE's high school, we were introduced polynomial equations. So today we will be using those polynomial equations of different orders and during this georeferencing. Other techniques like least square fit, overlay or Boolean's logic, set theory or your interpolation techniques. So basis of basically GIS is mathematics, and what people have done through computer scientists, we have got all these tools which are related with GIS available on different GIS platforms. But the fundamental of course will remain same, and these are coming only from mathematics. So let us move now for the georeferencing. Why basically georeferencing is required? As you know that when data is acquired, especially by satellite which are orbiting the earth, like Earth resources satellites, for example, starting with Landsat, our own Indian satellite series like IRS 1A, 1B, and it continues, then Cartosat and ResourceSat and many such our Indian satellites. If I talk about Landsat, then Landsat 8 OLI series is the latest in the series, and there are Aster satellites, Sentinel satellites of European Space Agency, and various such satellites, and data is available, and when they acquire the data, basically they are covering a curved part of the earth. This you have to remember that when we handle maps or satellite images, we handle them as a 2D, but when image is acquired by these satellites, it is in basically 3D. So which represents, originally it records the 3D part of the curve, and then we try to fit or make it as flat. And when we do it, and plus when satellite moves, these are the moving objects. So it is not necessarily that they will move exactly how they have been designed in their orbits. Sometimes there are other movements also, which we will also discuss. So because of these reasons, and one more reason is because of skewness, which we will also discuss in detail. So because of these reasons, a satellite image, when it is acquired by these satellites, will have these distortions, one, and these images will not have geographic coordinates. They will have a kind of image will always have its own origin, which is on the top left corner. And whereas our maps and other things, we assume that this origin, or in geometric coordinate system, the origin is from bottom left corner. So this, because of this complication also, we require georeferencing. So commonly this data, raster data or satellite images are acquired, and as you know that digital elevation models, most of digital elevation models which currently we are using and which is available on net, all of them have been created using satellite images. So there also georeferencing becomes very, very important. So this thing, and when we want to use our satellite data and their derivatives like land use map or lithological map or forest cover map or soil map, which are derived directly from satellite data, along with other data sets which are in georeferencing or in geographic domain, then we need to also do our georeferencing, and this will allow us to build up a coherent GIS database if we perform this georeferencing. Another important point with georeferencing is a common technique between remote sensing, digital image processing and GIS. So, it is a same technique which is applied for satellite images, same technique we can also apply for a scanned map, and that way we can also do the georeferencing. Many times we have to digitize from a topo sheets, like in India we do it with Survey of India topo sheets, and they may be available in analog form. So, when we scan it, they are in geometric domain. Now, we have to transform through this georeferencing process from geometric domain to geographic domain, and then that image or that image on which we will be working might be digitizing like contours and other features. So, everything will come then in geographic domain, because we have already georeferenced that image. So, this process is very important to transform a data which is maybe in geometric domain into geographic domain, and this entire process we call as georeferencing. And why we need, as I have mentioned, because other sources of data may not be directly from satellites, they might be already geographic domain. So, in order to have a coherent database generation, GIS database generation, we need to do this thing. Now, another complication may come about the map projection. This part basically map projection itself is a subject, and now our GIS softwares are capable of converting from one map projection to another without much problem. However, little bit errors introduction would be there, but if we are covering a very large area, if an area is not large, then that issue will not come. As I was mentioning, that like a flat surface, because the image data may be representing a curved surface. Through this process, what we do, we try to represent the data into a flat surface, and for that also sometimes people call as reverse sheeting, because we treat a digital image representing a curved surface as reverse sheet to make it flat, and the concept it will remain same. So, now we can define what exactly georeferencing is. That georeferencing basically transform images or maps, scanned maps or images which are in geometric coordinate system to geographic coordinate system. Now, in order to perform this thing, we use either base map or image having geographic coordinates, or maybe some library which might be available to us. So, if we are having a good library of ground control points, or in short we call GCPs, so if we are having that library, we can also access that library. So, this reference how individual cells or pixel will be transformed from geometric domain to geographic domain, for which we require a reference, and that reference may come from a base map or already a georeference image or a map, or maybe sets of or a library of GCPs or ground control points. So, by which we can achieve this geographic coordinate system for our data, input data originally which may be in the geometric coordinate system. Now, when we georeference data, raster data especially we are talking, vector data can also be handled in the similar way. But most of the time in this discussion we will be considering raster data, because it has got more complications. So, basically what we assign the coordinate system, geographic coordinate system, and by which involves basically 3 steps, which we will discuss how it is done, and in demonstration also we will be seeing how it can be done. So, georeferencing basically of raster data will allow us view query and analyze with other geographic data only if the data has georeference now. So, now the 3 steps which would be there. So, in that first step there are 3 steps, like first is registration, and then finding out the transformation function, and third one would be resampling. But before that we have to understand that what are the distortions which may be introduced while data is being acquired either by satellite or by some other sensors. And nowadays if you recall the history of remote sensing, you would find that initially remote sensing started with some towers or like balloons, airborne platforms, and slowly through aircrafts, and then we went to the satellites. Now a sort of I call as a reverse process has started again, that now a lot of remote sensing is being done as per requirements by using drones or these unmanned vehicles, and these vehicles are having capabilities of carrying a very sophisticated payloads and which can provide data also, a good satellite images of very high resolution covering maybe a small area depending on the requirements, and when one requires, that is the advantage, because satellites will have their own fixed overpass time or dates, whereas with drones the biggest advantage is that with drones we can acquire data whenever we want. So, that is why lot of emphasis is nowadays is on this, how to employ drone in remote sensing. So, when you acquire images from drones are again moving platforms, may not be very stable, and therefore they may also introduce lot of errors, geometric errors, which might be because of scan skewness. This is more prevalent in satellite images, maybe panoramic distortions if drone or satellite is at a very high altitude of the platform. This reason may be less in case of satellites, but it is more in case of drones, like change in velocity of drone, the change in altitude of drone within when the image is being acquired or data being acquired, then the pitch, roll and yaw, these 3 we will also see what are these. So, what happens basically that when earlier we had these optomechanical scanners, and they were doing scanning like this. So, we had this cross stack scanner distortions. So, if somebody for chain detection studies which is involving more than 40 years of data like Landsat 1 or 2, then one has to remember that they were suffering, those images, raw images were suffering from cross stack scanner distortions. So, when we do the georeferencing, almost all these geometric distortions are removed to a large extent. So, that is why this georeferencing is very much required. Now, as I said that these satellites were optomechanical satellites. So, there were velocity of the mirror also, and that you might be varying, and if it is not following the normal velocity path and if it is going like this, it may introduce geometric distortions. Now, scan skewness is still persist in satellite images because these are near polar orbiting satellite, and as you know that Earth is not perfect spheroid, and because of that and because of these designing of orbits, the satellites are taking images in a such manner that when say suppose it is taking 10 minutes to acquire one image. Now, between that 10 minutes Earth will rotate, and anyway the orbit is also not exactly from north to south, but it is having say roughly 9° angle in many cases, and it is moving around the Earth like this. So, if it is moving and in between the Earth rotates, this will bring this error in a large form which is called scan skewness. This error too can be removed by employing georeferencing. Now, when I was also mentioning about the raw yaw, these three altitude variations and other things, how they affect, how in the images. So, let us see, like when earth rotation is there, this skewness is there, and we expect that image should have been in this form, but it is coming like this. Similarly, altitude variation, if suddenly the spacecraft or aircraft or drone changes its altitude, this kind of distortions might be there. The expected one is the dashed line, whereas the image here the altitude has gone high, and therefore it is covering a large area, but at a smaller scale, and here altitude has come down and bringing basically altitude distortions. Now, pitch variation, when it tilt towards suppose the aircraft is going like this or your drone and suddenly it dips like this. So, if there is a pitch, again there will be distortion. A spacecraft velocity, suddenly it changes the velocity, again there will be error. And roll, if it rolls like this on which is perpendicular to the direction of the orbit, then it may bring a error, something like that. That the image would be representing this like this, whereas we expect a dashed line area. And if there is a movement like this on a vertical axis while the drone or spacecraft is moving, then you may be acquiring an image like that. So, these may bring lot of geometric errors, and to identify that whatever the errors which I am seeing in satellite image is because of that particular reason is really very challenging. So, the best solution is whatever the distortions any image or map is suffering from, and do it remove it through the georeferencing process, and that way we can achieve a geographic coordinate system instead of geometric coordinate system, and we can get rid of all these distortions. There are other ways I can also explain that this is how, this is the flight direction, and when air this is the grid suppose on the ground just to test it. So, it should have been acquiring data like this, that each pixel should be square in shape, that is what we know as the raster, and especially in case of images also, that the cell has to be the pixel has to be always square in shape. So, this is the ideal condition which we would to prefer, but if there is a scanner image, what happens on the margins, because it is not a for the margins it is not particularly nadir viewing, but off nadir viewing on the side like this, and this will bring distortions in my images. So, that is why these are, instead of covering a squared area, they are virtually recording a rectangular area. Of course, the image will always have a square unit. Now, when roll distortion is there, as here shown here, that roll is something like this. So, when roll distortions is there, it will record an image something like this, and if then crab distortions is there, because of wind there might be shifting also, which is called crab distortion. So, that may bring distortions like this, and if it is pitch distortions, it dips like this, then or like this, then again you may have some. So, across trace scanner distortions introduced by platform altitude variations, these will bring lot of geometric errors in our images. So, where each as you know that in raster each pixel in image has a row and column number, and also I told you that the origin of the image is always from the top left corner. So, first row first column we start addressing from there, but in this is in geometric coordinate system, but in geographic coordinate system we always start from bottom left. So, this is another adjustment we have to do during georeferencing. So, in order to, as we know that in order to display and analyze images with other data sets in our GIS database which are already georeferenced, it is essential to establish an image to word transformation, basically which is what is georeferencing, which converts your images coordinates. Image coordinates are starting from top left first row, first column like that, to the real world coordinates, which are our geographic coordinates. And this, as I have said in very beginning, that georeferencing is also called in literature geometric corrections or image registration, or sometimes people say, rubber seating adjustment. So, here what images with a common method of georeferencing, which involves the images to be statistically find a polynomial of a given order, polynomial equations which we have learned in our 10+2 or in high school time, that minimizes the error in a transformation from the original image coordinates, which are starting from top left, to the rectified image coordinates, which are in geographic coordinate system. So, like this we can perform georeferencing. Now, in order to perform, the first step to do the registration using ground control point. So, transformation of this image will be found by performing a least square fit for the coefficients of a given polynomial using ground control points, GCPs, that are picked by the users, and this is what we have to provide interactively. I am presenting a schematic here. Here we are having an input image, and this is my reference map. So, I call as a master, and the left image, the input image, I can call as a slave image. So, now this input image has to be georeferenced to our master image or master map. How it is done? This is just GCPs are shown in the form of cross, and these we call as ground control points. Now, this function polynomial transformation functions are there, which we will found through least square coefficient, and once ground control points using common ground control points, that means the same point which I am seeing in my image also in my master map, which are called the GCPs or ground control point, which has to be common. For example, there might be a crossroad which I am seeing in my satellite image, and the same crossroad I am also seeing in my reference map. That can become my one GCP. Now, there may be a GCP like a bridge on a river, that may be also a GCP. A bridge on the railway track or rail bridge on a stream or a river, that can also be taken as a reference. Any point which with the time which does not move can be considered as a reliable GCP. But the points like a bending of a river in a plain area should not be taken as a ground control points, because as you know that river migrates generally in flat areas. So, if I am that age difference means the time difference between input image and reference map is large, then there are chances that I might be collecting a wrong GCP, and the wrong GCP means I will have a wrong registration, wrong coefficient, wrong transformation, and ultimately completely incorrect georeferencing. So, we have to take care about that part, that when we collect GCPs, we should be very careful that I am seeing the both that points control point which should be common in both the images. And once I have found the transformation function, that means from the input image a single individual pixel where exactly it will go in the master image or master empty frame, that is decided through the transformation. The third part comes then, that what would be the value, pixel value from original image to the blank frame, which has been already referenced with the master map. So, now the pixel value I can have the original pixel value, or because of other accuracy purposes I can have some modified average, weighted average pixel value, and that process is called resampling. So, 3 steps. First is the identifying GCPs and registering them with master map, finding the polynomial coefficient, transformation function, and then finding the pixel value. And once these 3 steps are completed, we can achieve a georeferenced image, which will fit with our other data sets which might be available in my GIS database. So, this is how we perform. Now, which polynomial equation which order of polynomial equation I should choose, that will depend on the how much distortions my image is presenting. In this what you are seeing, this is my original data. Now, if it is just transformation from geometric domain to geographic domain, for example, this is my master image and this is my the image to be georeference. So, if I am just transforming from geometric domain to geographic domain, then I consider as a first order polynomial or conformal transformation would be sufficient. If my image required some rotation and change in scale, that this input image in order to fit with my master image, if it requires rotation as well as change in scale, then I would choose the second order of polynomial, or also called in literature you may find for first order conformal transformation, or in second order you find affine transformation. Now, there might be even a situation where we need a transformation, we need a change in scale, we need a warping, because my image is covering a large part of the earth, and that is because it is representing the curved part of the earth. So, instead of that curved part, I want to make it as flat. So, therefore, this warping issue will also come. So, transformation, rotation, change in scale and warping, if all these 4 processes are there, 4 requirements are there, then I will go for the third order of polynomial equation. Now, mathematically we can go, I have seen some GIS softwares where they allow you to go up to even 12th order of polynomial equation. But basically in our case in GIS we do not really require to go beyond third order. Why? Because whatever the distortion, geometric distortion which might be present in our maps or satellite images, they can be maximum of only third order transformation, they can be resolved. All those distortions can be taken care only by third order. Second point is that as you move higher in order, more the control points would be required. And sometimes if a image is representing a like forest area or a desert area or a snow covered area, then finding reliable common ground control points in my input image and master image becomes really very challenging, very difficult. So, unless until it is required, one should not always even resort to the third order. If suppose I am covering a small area of the ground or earth, then maybe second order of polynomial would be sufficient. So, what is the way I would know beforehand how much minimum number of GCPs are required against different order of polynomial equation. So, there is a very simple formula that p plus 1 multiply by p plus 2 divided by whole 2, and p is basically order of polynomial. So, like here if order of polynomial I choose 1, then minimum ground control points are required only 3. If I go for second order of polynomial, then I require minimum 6. Minimum does not mean that I will collect only 6. No, this is not a good practice. So, in my experience and understanding, and to achieve a better georeferencing, or people say within pixel georeferencing accuracy, then it is better to multiply by 3. So, if first order, then we should collect 9, if it is second order then 18 and likewise. So, if I do not require, for example, if I do not require more than third order, why I should go? Because most of these geometric distortions might be introduced by the satellite images or drone, can be resolved maximum up to third order in most of the cases. If really situation like in case of drone situation have been wind speed and other things, still image has been acquired, then probably fourth order may be sufficient. But again, finding reliable common ground control points in both images, input and master, may be very challenging. So, one has to be very judicious about choosing a polynomial equation, one, and accordingly also choosing very reliable common ground control points. So, once this transformation is found through this order of polynomial equation, then it is applied to every pixel, because now every pixel from input image has to transform to a new location in my which is you can imagine a empty wire mesh kind of situation. So, every cell of that wire mesh has to be filled with a pixel value. Now, that pixel value, as I have said, may be original or may be averaged or weighted average, that we will decide little later. So, the order the other operation which we perform doing a transformation of this type is determining the pixel value, and this is accomplished through using resampling techniques. And these when we have been discussing this raster data compression technique, at that time reference to these techniques also came, nearest neighbor, bilinear and cubic convolution. And at that time I mentioned that later on when we will discuss georeferencing, we will discuss these things in detail. So, today is the right time to discuss these things. Now, the transformation of these polynomial order of given order like here m is such can be expressed in these two equations. Basically, what we are trying to find out, the x dash, they are the new location in form of x and y against the input location of a distorted image or image which is in geometric coordinate system. So, by providing the input from the image coordinates, we are trying to find out the new location for all these pixels through these two polynomial equations. So, this is the common equation where m value can be replaced with the number of the order of polynomial. Now, if I take the example of ArcView and ArcGIS also, and that the image to word transformation is a 6 parameter affine transformation, and that is basically a second order of polynomial equation in the form of very simple that as you go higher in order our equation polynomial equation becomes much complicated. So, in case of second order, what second order will do, that it will transform geometric coordinate system to geographic coordinate system 1, and also it will allow us to rotate and maybe change in scale. So, when these three things can be adjusted, then second order polynomial is good. So, how it second order polynomial will look like, we are trying to determine the new location for pixels. So, ax plus by plus c and dx, e by and f. So, how these values will come, or here in the same equation, but instead of x1 y1 it is x dash y dash is given, and what we are trying that our coordinate system may be in meters or maybe in geographic coordinate, does not matter. So, this with these equations where we trying to calculate the x coordinate of the pixel on a map and also y for coordinate of the pixel on the map. X is the column number of a input image and y is the row number of the input image, because as I have said, remember that image coordinates start from top left corner here, and whereas our geographic coordinate system, the coordinate system starts from bottom left. So, that is why this is very important. Now, A will allow in this equation, A will allow the scale x scale dimension of a pixel in x direction. Then also we will have a by scale change, but it is negative. By scale will have negative value because we are coming from top to bottom because of different coordinate system which are followed in image and map. And then of course, rotation terms which is B and D here, and CF are the translation terms, x, y map coordinates of the center of upper left figure. So, when these things are resolved, we get a geometric correction. Now, why further explanation I would like to give about this, why this negative is, as I have already mentioned, that the bi-scale is negative because the origin of an image and a geographic coordinate system are different. Origin of image is from the top left corner, whereas a geographic coordinate system are in bottom left corner, and because of that bi is kept a 0. After this we will get the statistical this root mean square, and error we always try that it should be if suppose I am handling an image of 10 meter resolution, then my error should be less than 10 meter. So, then we call as within pixel accuracy. So, one always try with choosing a correct coordinate these ground control points, and also appropriate polynomial equation. So, in journal, the journal formula is derived and applied to the control point. A measure of error, that is the residual error, is returned. Now, when we use the softwares which has become very smart, and these modern software like ArcGIS or others, while doing this geometric registration, that means identifying ground control points and putting registering with the master map, at that time it will keep giving you the residual error against the total one, and also against individual points, ground control point. So, if you are not happy against individual collection of GCPs, you can delete it and again select another one, or maybe same with more care, and you can achieve better. So, it has become more interactive rather than a sequential one. This is the point which I wanted to bring, that rather than sequential, though our discussion looks like we are doing a sequential, but here it is not exactly sequential. As you keep collecting the GCPs, it will keep giving you the error information, and as soon as you realize that point number say 2 is having large residual errors compared to other points, and therefore your this root mean square is coming, total one is coming bad. So, you can remove the number 2 and recollect at different location, or maybe recollect at the same location, but with more care. And the error difference between where the point ended up as opposed to the actual location was specified, that is the point position. And these are nowadays the graphic has been introduced in this. So, you exactly also know on the screen, when we will see the demonstration, we will see that on a screen you exactly know that how much error, even in form of graph, red part, green part of a vector will be also visible. So, the total errors is computed by taking root mean square RMS, sum of all the residuals, to compute the RMS error, and that becomes our total error, which is has to may be there, which we have to manage. So, manage means here that if we can achieve this value, root mean square value, within the resolution, spatial resolution of satellite image, that is the best possible georeferencing one can achieve, because beyond that you cannot have a accuracy. So, this value, the root mean square, describes how consistent the transformation is between different control points, or also links in, like in ArcGIS, they also use word links between a slave map and master map, between input image and your target map. So, like here this link is shown here, that this is supposed to be here, but it is there somewhere. So, this is showing the example shows from a control point yellow cross placed on vector target data at a street crossing, this street crossing at and associated control point, that a green cross placed on the raster data set. The associated link is represented by the blue line joining the control points. So, this is what it is. So, this much graphically this error, the root mean square error, is being displayed here. So, if you are having say 20 points, any point which is showing the large value, automatically it is having a major error or largest error, and therefore, because instead of going through the numbers, you can see graphically and you can rectify that issue there itself. As I have been saying also in case of GIS, that error is very important part, because error propagates in GIS. And I have said that after each and every operation in GIS, check for errors, and if found, correct it, then go for the next. Do not leave error for other to correct it. So, that is why here, while doing the georeferencing or while doing this first step, that is registration of ground control points or registration of GCPs of your input image to the master image, whenever you see that any GCP is giving large error, just remove it and recollect it or go for a new GCP. Now, of course, these GCPs will depend, the requirement of GCP will depend on the complexity of transformation or order of polynomial, and how your image is. Like some drone images may be suffering from lot of distortions, and therefore, one has to be very, very careful with those. Most of the satellite images, as I have said, would be corrected to large extent using just third order of polynomial. So, adding more GCPs will not necessarily yield a better. That means like minimum, like for first order minimum 3 are required, or for second order 6 are required. So, I suggested through my experience they multiply by 3. But instead of if suppose 18 are required for second order and you keep collecting 50, that will not basically yield better registration or results. So, do not then waste your time. Minimum 6 required for second order, you can maximum you can go to 18, 16, something like that. And also one has to remember that GCPs should occupy the entire raster data set. What it means that if I am having this much area of image, that means my all control points should not be located here. They should be located in other places also. Like I should have a control point here, I should have a here, 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 here. So, if possible, GCPs should occupy the entire raster data set rather than concentrating on in one area like here, which is not good. And typically having at least one GCP near each corner. When I was drawing this, drawing, then I deliberately put all in 4 corners. So, one should try to put in the corners of the interior to get the best result. So, you start with corners, then put in interior, and think that you are handling a digital rubber sheet, and in order to fit a rubber sheet from one domain to another, you start doing. This is a analogy. Let me give you an analogy here before I move to the next point. If you might have observed how a shoemaker makes a shoe. So, he generally is having a flat sheet of leather, and at the same time he is having a wooden mold which is having a more or less shape of a shoe. So, what he does, that he takes first this flat leather sheets and start putting that leather sheet through nails over that the wooden mold. And first he will generally what they will do, either they will nail first at the toe side or on the heel side. So, suppose he has started from toe, then the next he will pull, and then he will do next at the heel, then on the sides, and slowly then he will nail the entire leather over that wooden mold like this. And so that it fits everywhere, and the leather, then they provide the heat, and then when this wooden mold is taken out of that curved leather sheet now, then it will remain in the same shape as it was targeted. What we are doing, almost exactly the same process we are doing, but we are doing digitally. Instead of leather sheet, we are having a distorted image which is in geometric domain, and our mold is basically the master image or master map, and these nails are nothing but the GCPs. So, GCPs like the shoemaker put nails all around, we should also do it all around and also in the center. So, when we treat our input image as a rubber sheet, then we can get a better results like that. So, that is why I gave this analogy. Lot of things in science or other domain comes basically from observations. So, one should be very interesting for taking such observations and try to correlate, find out the analogies in our, which will provide the better understanding. Now, let us come back to this discussion, is that when error is particularly large, this root mean square RMS error, you can remove and add control points to adjust the error. Whenever you see a particular point is giving large error, or 2 out of say 20 points, 4 or 5 giving are large error, remove them. And as you keep removing, your root mean square value will also keep changing. So, although this error, RMS error is good assessment of transformations accuracy, but do not confuse with a low RMS error with an accurate register. It is not necessary, because the transformation may still contain significant errors due to poorly entered control points. If control points itself which are common between input and are different, then there is a problem. More control points of equal quality used, the more accurately the polynomial can convert the input data to output coordinate. Now, we come to the last part of this discussion of georeferencing, that is resampling methods. Very quickly we will go through this. Now, in the background what you are seeing is my sort of wire mesh which has to be filled with pixel values, which would be coming from my this image, which is here, which is uncorrected matrix. Now, for each pixel, what I am value which I have to transform from here to the master grid, then what should be the pixel value? So, let me explain first here, then we will see further details. So, if for the center pixel I want to transform to the target, which is this one in my target grid, then what I will do, instead of doing anything, just take this value. Suppose this value is 75 pixel value. So, the same 75 is assigned to this in this master grid. So, this value, suppose this is 75, this is assigned to my master pixel. Same way I will keep doing for other pixels also. Now, when this situation is not there, and if I am having for example, if I am having another way of doing this, then what I can do, I can find out the weighted average, that this is my target area, target pixel area is this one, whereas these 4 pixels which are overlapping with my target pixel in different way. So, the one which is marked 3 here is occupying the largest area, this much, and the other one accordingly which one is occupying. So, I can use a weighted average concept, that whichever is having the largest coverage will have the maximum influence for my target pixel. It is the Tobler's concept which we also discussed during our this raster data compression techniques, and this Tobler's concept will also be discussed when we comes to this interpolation techniques. So, whoever is occupying or nearest neighbor, whoever is having the maximum overlap will have maximum influence while deciding the new pixel value, and then weighted average is taken and the new pixel value is determined and given to the that location, and likewise for each pixel this way the calculation can be done. So, the first one where no changes are done and as it is the pixel value is transformed is called nearest neighbor. The second one which I have just explained is called bilinear, where only 4 surrounding pixels generally will be involved. Now instead of taking 4, I can take 4 by 4 or 3 by 3 kind of this situation. And there then I will find out that which one is having maximum influence or which one is less. So out of these 16, these 16 pixels of input image would be considered to decide a new pixel value for my target image. And this way, this method of resampling is called cubic convolution. So we will discuss in detail about these and pros and cons also very quickly. The nearest neighbor resampling determines the pixel value from the closest pixel to the input coordinate. As I told you that the 3 in this one and the 3 will have the maximum influence. So that will carry forward to the new cell, and that method is called nearest neighbor, also shown here. Now this method is considered the most efficient procedure in terms of computer time, because no further calculation is required, just reading the value, pixel value, and giving to a blank grid. And note, therefore there will not be any modification in the quality of input image. Sometimes we have to keep the intact the quality, because if we do not want to compromise with the quality of image, then nearest neighbor resampling method is the best. However, there are some problems. This is the advantage, that does not alter the pixel values, but it is there may be some errors like into the corrected image because of jagged feeling it will be, or stair steps kind of thing. So corrected image may be offset especially by up to half pixel. So from georeferencing point of view, that may not be very accurate approach of resampling, but from image quality point of view, it is the best approach. Now there is a trade off. You are losing little bit georeferencing quality, but at the same time you are keeping intact the image quality. So you have to decide depending for which you are going to use such data. And as I have already said, that this corrected image will have the jagged or blocky appearance sometimes if it is coarse resolution, but if it is reasonably high resolution images, such issue will not come. Now the next method is the bilinear method, as I have already discussed, that it will take the weighted average of the nearest 4 pixels of the uncorrected image, and then will assign the new value to the final DN value or digital number or pixel value. So the closer the center point of the pixels, the greater contribution or weight it will have. So whichever the point which will occupy or having the less distance will have the maximum influence. This also happens in real life also, even in case of corona. So this concept is there. This is Tobler's theorem. Now there are advantages, disadvantages. So in this technique also, that bilinear sampling will generate a smoother appearance, though jagged issue may not come, as we have been discussing in case of nearest neighbor. So this will produce a very smooth appearance image, but may be blurring or loss of image resolution. So what it is doing, it is though providing better geographic accuracy or georeferencing accuracy, but at the same time it is reducing the image quality. So it is a compromise between georeferencing and georeferencing accuracy and image quality. So you have to choose again as per requirements. If you do not want, if you are ready to lose the image quality little bit, but you do not want to compromise on the georeferencing accuracy, then this method is quite good. Now as you can imagine that it has to take the weighted average of 4 surrounding pixels, and therefore generally the computation time it might be 4 times. See, for small images 30-second extra here and there does not matter, but when we are handling large images, then one has to be very careful about deciding these techniques. And highly accurate registration of course will achieve more faithful pixel values from original uncorrected image. This is true in all the cases. Now last this technique is cubic convolution, in which we are involving now 16 surrounding pixels of uncorrect image to approximate or estimate the pixel value of the new pixel in the corrected space, and by which, like here, all these orange dots which are shown here, they are all considered for the new pixel value. What are the advantages? That it is closer to the perfect sin x over x resampler than the nearest neighbor or bilinear sampling, and avoids disjointed appearance of the nearest neighbor. This jagged or disjointed appearance which might be possible in coarse resolution images, if they are subjected to nearest neighbor, those things will not be seen in cubic convolution. Of course, it will modify your pixel value, original pixel value, to a, basically it will corrupt your original pixel value. So, it is a more harsh word here, that it will corrupt your pixel value to a large extent, because in order to drive a new pixel value, 16 surrounding pixels values are considered depending on the distance, and then calculations are done. So, again it is a judicious statement has to be there, or as per requirements, that what you are basically trying to do with the output. So, if you are going for classification, that is image classification, then I would not suggest that you should go for cubic convolution, not even for bilinear. Then do not compromise on the quality of image and do not corrupt your original pixel values. Just keep them intact and go for nearest neighbor method. And of course, computation time compared to other two techniques is going to be much more. Compared to nearest neighbor, it may be more than 10 times. Compared to your bilinear, maybe 4 to 6 times. So, that is very important. One has to be very judicious in entire process, which polynomial order, how much ground control points, and then which resampling techniques one need to adopt. So, with this though this have been little longer, but in order to complete the discussion and keep everything in one presentation or one lecture, I thought that I will exceed the limit, but anyway, I hope you must have enjoyed this discussion. This is my very favorite subject within the GIS. Thank you very much.